Hello, and welcome back to part three of this multi-part series that I've been instructed to do as part of my course requirements. And in this part, we will be talking about two of the most important quantities or properties that we study in thermodynamics, which is energy as well as entropy. Okay. But before we get into this, I want you to understand the purpose of these formulas here. Okay. So one of the assumptions that we make when we're working with combustion reactions is that both the reaction mixture, so as well as the product mixture, are both ideal gases. And so what that allows us to do is use these formulas, which are, again, only applicable for ideal gas mixtures. And you can find values of absolute internal energy, absolute enthalpy, absolute entropy, among other things. Okay. So, but why would this be a reasonable assumption to make? The reason for this is that during combustion reactions, the temperature gets really high, right? And as temperature rises, we know the gases will start to behave more and more like ideal gases, right? And so this is why we can make this assumption without much issue. Now, in the next part, we will be looking at the idea, the central idea behind enthalpy of formation. Okay, this new quantity that we define. And now, what is the reason why for this new quantity? Why do we need this? So far, when we looked at things like Rankine cycles, for instance, okay, if you think back to Rankine cycles, if we wanted to find the work across a turbine, this is a very poorly drawn turbine, I apologize. But if we wanted to find the work across this turbine, all we had to do was look up the state before and find the enthalpy on a steam table, and then look up the state after and find the specific enthalpy after it passes through the turbine. And then we just got the the work output as this difference in enthalpy, right? However, what the issue that lies with combustion reactions is that when you have this reaction going on, it takes in these reactants, and in the product mixture, it changes them via chemical reactions. It changes them so that they physically don't exist on this side. Okay? So there has been a change in this hydrogen, in this oxygen, such that they're no longer hydrogen and oxygen, but instead they've bonded together into water. So you can't use that idea of a steam table anymore, where you had the same substance. Okay? For instance, in a steam table, we knew that it will still steam here and it will still steam here before and after the turbine, right? However, this isn't the case for a combustion reaction. We can't just use these property tables on their own. We need instead another value, which we call the enthalpy of formation. And now, what is this enthalpy of formation actually? Okay. Well, the enthalpy of formation, I would say the best way the way that I like to think about it is that it is the energy released. So it is the energy released when you form a given substance, let's say CH4, from its building blocks, from its elemental building blocks under standard conditions, right? So let's say you have a bunch of carbon and then you have a bunch of hydrogen gas, and they're all under standard conditions. If you react them together, the energy change that will be produced in the making of this methane is my enthalpy of formation. Okay. And now we will look at, okay, another problem that arises when we're using things like steam tables. Now, the thing is, with the steam table, the datum or the zero value for enthalpy and entropy were all set at an arbitrary point. Okay? It's all set at an arbitrary point. However, when you have this chemical reaction with, when you have this combustion reaction, you can no longer use the same datums because in our calculations, they won't cancel out nicely. So instead, what we do is, again, we define this enthalpy of formation, which gives us a new standard for zero. Okay? And what I mean by that is, since enthalpy of formation is just the energy change when you make a substance out of its elemental building blocks under standard conditions, well, the enthalpy of formation of, let's say, hydrogen and oxygen will just be zero, as you can see in this next part. An enthalpy datum for the study of reacting systems is established by assigning a value of zero to the enthalpy of carbon, hydrogen, nitrogen, and oxygen. And in fact, any other stable element at the standard reference state will be at zero enthalpy, we're saying. Okay. And now what is the standard reference state? So the standard reference state just happens to refer to these specific conditions at 25 degrees Celsius and 1 atmosphere of pressure. And if we were working with solutions, we would also include the concentration at 1 m. But since these are all gases, we don't really have to think about this. The enthalpy of a compound then at the standard state equals the enthalpy of formation, which we denote with this symbol. Okay, this little O is for the standard state, and this little sub F is for formation. Okay, and so to the next part, we basically look at table 825, which lists all these values of enthalpy of formation. Okay, and now recall what I just said about my elemental building blocks. They will all be at zero enthalpy. So they're all at zero. However, let's say carbon monoxide, okay? To form carbon monoxide, I have to make carbon react and oxygen react. And when I make these two react, it releases energy. It makes carbon monoxide, but it will also release a little bit of energy. And we denote this with a negative sign. As you can see, if you can, well, it's very small, but I hope you can see the negative sign that's there. And this is the standard that we use. Whenever you have an exothermic reaction, you use a negative sign to indicate that energy has been released. And now you can say the same thing for something like hydrogen. So when you have a hydrogen molecule and trying to make hydrogen atoms, well, obviously you're going to need an energy input to break the bonds down, right? To make these atoms. And so certain substances actually require an input of energy. And so their enthalpy of formation is positive, as you can see, is positive here for oxygen atoms, and it's positive here for hydrogen atoms, right? And this relates back to the idea of an exothermic reaction, which you think of as a minus sign, and an endothermic reaction, which you consider to be a positive value of enthalpy. All right. And so for the next part, we take these ideas so far that we've seen of enthalpy of formation, right? And we can now define the absolute, we can start to define the absolute entropy of substances. by adding the formation enthalpy as well as the change in the enthalpy from my standard state, to whatever specific state that I have, right? And so what's interesting is that for this delta H, I can just look up my steam table, my ideal gas table, or any other table as appropriate, because in that case, that arbitrary datum gets canceled out. So it gets canceled out from, let's say, H1 to H2. Well, the arbitrary datum gets canceled out. So what you get as the delta H value will hold even for this absolute enthalpy value. So this is how you get your values of enthalpy essentially for these combustion reactions, right? And for this next part, we can quickly look through this example where they use this formula. As you can see, they first bring up the energy balance formula. And these ends, well, these are the, well, n dot just happens to be the molar flow rate, I believe. And so all these will be relative or in ratio, or rather, we can say per mole of the fuel, right? So let's say you have 1 mole of fuel going in, and you have, let's say, 1 mole of CO2 being released, right? So that would mean that this n dot and this n dot would be the same, right? And now another assumption that we've used here is that the kinetic and potential energy effects will be neglected across this control volume that we have here for our chemical reaction. And so from there, it's just a bunch of basic calculations. As you can see, they've divided by n dot c, which will happen to be the molar, or rather, the molar, again, yes, the molar flow rate of the fuel. So here, well, okay, so for this particular reaction, the ratios are very nice. They're all 1 to 1 to 1. And so they're all equal, right? And so you get some nice cancellations here. And so moving on, you can simplify this whole reaction further to equation 1. And then you can use table 825 to then sub in the value of the enthalpy of formation for carbon. And you will find that it is 0 because it is in the elemental form. And you can use table 823 for oxygen to get the enthalpy values for oxygen. And actually, you can find the relative values again, the delta H, because the enthalpy of formation for oxygen is already 0, is the change that really matters here. And we first look at the standard state, which would be 298 Kelvin, and then the state that it is in before it goes in, right? At 400 Kelvin, 1 atmosphere. And so you get this delta H, which is this. And the last value that we need is the enthalpy for the CO2. This is quite easy. You first look up you first look up at table 823 for carbon dioxide. You look at the change. So from the standard state to the state at 500 Kelvin, where it is after the reaction takes place. And you use table 825 to find this enthalpy of formation. You add these together, you will get the enthalpy value. And since you have all three enthalpy values, you put this in, and you will essentially find the, well, the energy change, right? And so this was a basic example of the calculation. And I believe this is it for this video. I will cover more things in the coming videos. Thank you for watching.